Yesterday we were in section 5.3. We were close to done, but not quite done, so let's finish that one up first, and then we'll move on to 5.4. So here's where we were yesterday in 5.3. We had if f of x and g of x are inverses, then we had this interesting rule for derivative. The derivative of g of x is 1 over the derivative of f evaluated at g of x. And I think yesterday we did an example where we had a function where we could not find its inverse, but we could still evaluate its derivative. Here's another thing you can use this for. I'm going to pick a function I like a lot. F of x is sine x. Does sine x have an inverse? Not cosine. When you say sine to the negative 1, is that negative 1 a power? Is that we use that little negative 1 notation to stand for function inverse too, don't we? All right, so typically we write g of x is sine inverse of x, but that little negative 1 there, when we're dealing with sine and cosine, does not stand for negative 1 power. It stands for inverse. So instead of that symbol, I personally prefer arc sine x, because then there's no doubt about it. There's no question about whether it's a power or an inverse, or what it's an inverse, it's arc sine. But I have a bigger question than that. Sine isn't 1 to 1, is it? No, definitely not. Not even close, is it? Your sine graph looks something like this. So is it 1 to 1? Well, not the period, but depending on the interval you pick. The sine graph on its own is definitely not 1 to 1. In fact, it fails being 1 to 1 almost as badly as you can, because that horizontal line right there crosses how many times? An infinite number of times. It fails the horizontal line test about as bad as you can fail it. So once again, just like we did yesterday with our x squared function, we need to limit the domain. And so we want to limit the domain to force this sine function to be 1 to 1. At the same time, we will also want to get all of the y values that we can. So there are lots of different ways to limit the domain to make sine 1 to 1. Anybody have a good choice?
0 to 2 pi.
What's that?
0 to 2 pi.
0 to 2 pi wouldn't work, because 0 to 2 pi would go from here to there, and that's not 1 to 1, is it? It would cross twice. Negative pi halves to pi halves is the one we pick. This is the point right here, negative pi halves, comma, negative 1. And that right there is the point pi halves, comma, 1. So typically when we're talking about sine and we want to talk about its inverse, typically you use that domain. So our domain for sine, in order to write this arc sine function, x has to be between negative pi over 2 and pi over 2. Questions on that? All right, now, here's the whole point. What's the derivative of g? What's the derivative of arc sine of x? Do we have a formula for the derivative of arc sine of x? No, we don't. We're about to make one. According to this, it's 1 over the derivative of f evaluated at g of x. So that's 1 over. I take the derivative of sine. What's the derivative of sine? Now, what's the derivative of sine?
Cosine.
Cosine. The derivative of sine is cosine, and then I have to evaluate that at my g, which is arc sine. So the derivative of arc sine of x turns out to be 1 over cosine of arc sine x. Nice formula, huh? Apparently you're not too impressed.
Should you rewrite that as secant, or does it not matter?
I could write it as the secant of the arc sine of x if I wanted to. That looks a little bit more simple maybe because I don't have a fraction involved too. I could write it that way, absolutely. Other questions? You don't like fractions? Let's see if you like this. What does arc sine do? Okay, so what kind of numbers, if I want to use my arc sine function, what kind of numbers can I plug into it? And what kind of answers am I going to get back when I plug them in? Well, what kind of numbers do you plug into the sine function? For sine, you plug in numbers between negative pi over 2 and pi over 2. And those are angles, aren't they? So for the sine function, you plug in angles, and what do you get back? What do you get? Like, what's the sine of pi over 4? It's root 2 over 2. You get a number. That's exactly right. So when you're using sine, the things you plug in, you're plugging in angles. You might plug in pi over 6. That's another nice angle. What's the sine of pi over 6? You say it with confidence. 1/2. That's correct. So when you plug in angles, you get numbers. What sort of things do you plug into arc sine then?
Numbers.
You plug in numbers, and the answers you get are angles. All right. So arc sine of x, when I plug in a number, I'm going to get some sort of angle. So I'm going to call that angle theta. Theta is arc sine of x. I don't know what angle it is, but I know it's some angle. For example, I might plug in for x, I might plug in 1. So if x is 1, what's arc sine of 1? The sine of what angle gives you the answer 1? Pi over 2. Pi over 2 would be the right answer. All right, so I'm going to take this theta equals arc sine of x, and I'm going to do sine on both sides. On the left-hand side, I get sine of theta. On the right-hand side, I just get x. How come I just get x on the right-hand side? Sine and arc sine are inverses. They cancel each other out. So, all right, now I'm going to draw myself a nice little picture here. So here's my angle theta. I remember that sine is opposite over hypotenuse. So sine of theta is x over 1, opposite over hypotenuse, x over 1. Then I go talk to Pythagoras, and I use his theorem, and I can figure out the length of the other side. It would be square root of 1 minus x squared. All right, so where am I going with this? Well, where I'm going with this is secant of the arc sine of x is the secant of theta. That's what I called arc sine of x. I called it theta. And I look at this pretty little picture here. What's the secant of this angle? How do you find secant? It's 1 over cosine, and cosine is adjacent over hypotenuse. So it's going to be hypotenuse over adjacent. So we can do some fancy trig and a little bit of algebra and we can make the derivative of arc sine look like kind of a nice thing.
Still not nice.
But I think it's better than secant of arc sine of x. I'm not saying it's wonderful, but I think it's better. So this is a formula for the derivative of arc sine.
We ever need it when you give it to us? Or no?
Eventually you'll need to know it. Section 5.5, I believe, is all about inverse trig functions. So we'll come back to this and we'll do this again. And we'll do it for arc cosine, and we'll do it for arc tangent, and we'll do it for all those wonderful inverse trig functions.
Did the hypotenuse of one come from you saying that
Well, I just thought of x as being the fraction x over 1. So I chose to make my hypotenuse 1. It makes it a lot easier. Other questions? All right, my last example of this. I'm going to let f of x equal ln x. Does ln x have an inverse? Does ln x have an inverse? Yes or no? 50-50 chance of being right.
No.
No, you're wrong. Why does f of x equal ln x have an inverse?
Because it's one. It's 1 to 1.
And how do you know it's 1 to 1?
Always increasing.
And how do you know it's always increasing?
Because there's a vertical asymptote at 0.
And more importantly, there is a vertical asymptote at 0. The way that I know it's always increasing is I looked at its derivative. Its derivative was 1 over x. And remember, right from the beginning, of course, ln x is only defined for positive numbers. So since f of x is ln x, and by definition x can only be positive numbers, the derivative is 1 over x. The derivative is always positive, which means the function is always increasing, which means it is 1 to 1, which means it does have an inverse. What's its inverse?
E to the f.
Its inverse happens to be e to the x. And that's the next section. So this is a lead-in right into the next section. The inverse happens to be e to the x, and that's what we're going to define it as in the next section. You probably know that from pre-calculus days, that those are inverse functions. All right, so I'm now going to do, just like I did for the arc sine, I'm going to figure out a formula for the derivative of e to the x. I think you'll like this formula better than you like the sine formula, but you'll tell me when we're all done. All right, so if g of x equals e to the x, then g prime of x is 1 over f prime at g of x. So that's 1 over, if f is ln x, what's f prime? 1 over x. So what's f prime at g of x? 1 over e to the x. Simplify 1 over e to the x. It is e to the x. So what's the derivative of e to the x? It's e to the x. So that's a very unusual function. G of x equals e to the x. G prime equals e to the x. E to the x is its own derivative. It doesn't happen very often. I can only think of one other function that has that property. Can anybody tell me another function where you take its derivative and you get exactly what you started with? It's a lot easier than you think.
0.
0 is the only other function that I know of that works.
Awesome.
When I take the derivative of 0, I get 0. And those are actually the only two functions where that works, where the function is its own derivative. All right, so that brings us right into section 5.4. Section 5.4 is all about the function e to the x. We define the inverse of ln x to be e to the x. For the function ln x, whoa, what was its domain? Forgot to turn the sound off my phone today. What was the domain of ln x?
All positive.
All positive numbers. X is a positive number. What was the range of ln x? All numbers, negative infinity to infinity. What's the domain of e to the x? Why negative infinity to infinity?
Because it's the range we're talking about.
What do inverses do? Inverse flops the x's and the y's. So if the range of ln x is negative infinity to infinity, then the domain of e to the x must be negative infinity to infinity. And in a similar manner, what's the range? Y is greater than 0. All right, there's your domain and range. There's your first fact. Second fact. E to the x is always increasing and concave up. How can I prove to you that e to the x is always increasing and always concave up?
First and second derivative.
Take the first and second derivative. All right, so if f of x equals e to the x, then the first derivative of e to the x is e to the x, and the second derivative of e to the x is e to the x. This just became my new favorite function. Taking its derivatives is so simple. Can't screw it up, can I? How does that prove it's always increasing? What's that? It's positive, because we just said a second ago e to the x is always positive. So the derivative is always positive. It also proves it's concave up because the second derivative is always positive. That's the range. All right. So from that information, we know some information about the graph. What does the graph of e to the x have to look like? Its domain is the domain is all real numbers. We can only have positive values. It's got to be increasing and concave up. What could it look like?
The positive half of a parabola.
Kind of like the positive half of a parabola over here. But what's it do for negative values of x? It can't turn around and go back up, can it? Because then it would be decreasing. So what's it do? It goes like that. Keeps decreasing if you're going backwards.
Is it increasing?
Okay, increasing forever. Correct. It's increasing forever. That makes sense. Because what did the derivative of ln x look like? I'm sorry, what did the graph of ln x look like? I said derivative. What did the graph of ln x look like?
Kind of like y squared kind of thing.
It looked like that. So ln x had a vertical asymptote. So it would make sense that its inverse would have a horizontal asymptote because, again, inverses interchange x's and y's. ln x had the point 1, 0, and e to the x has the point 0, 1. Again, x's and y's are simply interchanged. Okay? Questions on that? All right, so we got a little bit of algebra to do here, and then we'll do some more calculus. How do you solve, this is known as an exponential equation. 5 times e to the 3x equals 20. Why is it called an exponential equation? It does increase exponentially, that's true. The variable is in the exponent. When you have variables in the exponent, those are known as exponential. As opposed to something like this. That one's not exponential. What kind of equation is that one? That one's quadratic. Okay? But that's the difference. When the exponent is in the variable, they're called exponential. All right, how do you solve exponential equations?
Divide by 5.
You divide by the 5 first. And then you said do what?
Take the natural log.
Take the natural log on both sides. You can do that because natural log is a one-to-one function. Since natural log is a one-to-one function, when you do natural, if two things are equal, when you do natural log, they're going to be equal. And how does that help? What happens on the left-hand side? The ln and the e are inverses. So you're left with 3x equals ln 4. So x is ln 4 over 3. One more maybe. How about, I don't know, anybody got a hard one? You want a hard one? Yeah, you want a hard one? All right. I like when people want hard ones. E to the 2x minus 2e to the x minus 3 equals 0. How do you solve that one? Take the 3 over. Okay, I can move the 3 over. It's not wrong. Then what? Natural log both sides. I can do that. Unfortunately, it only helps. Why not? Can I simplify this left-hand side at all?
Yeah, you can divide by 2.
ln 2x over 2e to the x.
All right, you got to be careful. If this were ln e to the 2x minus ln 2e to the x, then I could switch it to a division. But unfortunately, it's not log minus log. It's log of an entire quantity with a subtraction in the middle. So unfortunately, the rule you're trying to use doesn't work.
But when your bases equal, couldn't you do something with your exponents if your bases were the same? Or no, am I thinking?
No, you're on the right track. All right, so what we've done here, we didn't do anything wrong, but we didn't do anything helpful either, unfortunately. Let's try again. And Samantha's on the right track. This has something to do with the bases being the same. They both have base of e. But this one has an x and that one has a 2x. So they're not quite the same, but they're related. How is e to the x related to e to the 2x?
Get rid of the e or something, don't you? Just put it down the exponents or something like that.
Yeah, I don't remember either.
Yeah, I really want to get rid of the e's. The e's are the bad parts.
Forgot how to do it.
If you had everything with an e to something, couldn't you just take the exponents off of it and cancel out all the e's?
Correct, but I don't think there's any way to get that number 3 with an E in it, unfortunately. That 3 is the problem. All right, well, here's the deal. What happens if I take e to the x and I square it? That's e to the 2x, isn't it? Because when you have a power followed by another power, what do you do with your powers? You multiply them. So this, on the left-hand side, this is e to the x squared minus 2e to the x minus 3 equals 0. Just for a minute, pretend that this is an e to the x here and this is an e to the x there. Pretend that they're just the letter y. What would you do if you had y squared minus 2y minus 3 equals 0? You would factor. It's a quadratic equation. That's exactly what we're going to do here. Except we're not going to have the letter y. We're just going to have the symbol e to the x. So this is going to factor as e to the x minus 3 times e to the x plus 1 equals 0. See, I told you this was a hard one. That's a weird sort of factorization that you don't usually see. You don't usually think of e to the x being squared to get an e to the 2x, and then that this is really a quadratic equation in disguise.
Well, both ones, right? Not gonna work, right? 'Cause it's not.
One's not going to work, but one of them is. That's correct. So what do I do now? I set them both equal to 0. E to the x minus 3 equals 0. E to the x plus 1 equals 0. This one over here gives me e to the x equals 3. I can do ln on both sides and solve that one. I get x equals ln 3. But this one over here, I've got a problem. I have e to the x equals negative 1. I can't do ln on both sides, can I? Because I can't do ln of a negative number. So that one doesn't work. Only get one answer. Questions on that? All right, so that's exponential equations. How about solve? ln of x minus ln of x plus 1 equals, make that number you like, 13. All right, so that's a logarithmic equation because it's got logarithms in it. How do you solve logarithmic equations? You want to do e's eventually. Can't do e yet though. You need to do something first. Combine the two ln's. These two ln's are connected with a subtraction. I can combine them. I'm going to write this as ln of x over x plus 1 equals 13. And now I can get rid of that ln. How do you get rid of an ln? Well, it's not times by e. It's really, this becomes your base. So you're really going to have e raised to the ln x over x plus 1 equals e to the 13. And then what happens on the left-hand side? Why do we use e? What do e and ln do? They're inverses. X over x plus 1 equals e to the 13. You weren't supposed to pick 13, by the way. You were supposed to pick 0, because e to the 0 would be 1. That would be easy to work with. But you picked 13. We're stuck with it now. So how do we solve this equation? When in doubt, always pick 0. Well, if I take the natural log of both sides, I'm going to be right back to where I started. I could do that, but I don't want to. That's going backward. I think what I want to do is I want to get rid of this fraction. So I'm going to multiply both sides by x plus 1. So I'm going to have x equals e to the 13 times x plus 1, which I'm going to write as x e to the 13 plus e to the 13. I'm going to distribute that e to the 13 through. Yeah, I'm getting close. How do I get the x all by itself? I've got two of them still. What do you do when you have an equation and you have x's on both sides? You move one of the x's over, you get all the x's together, don't you? So I'm going to take this x right here and I'm going to move it to the other side. That becomes x minus x times e to the 13 equals e to the 13. Now that I have all my x's together on the left-hand side, factor out an x. X times 1 minus e to the 13 equals e to the 13. Finally, I divide. So x is e to the 13 divided by 1 minus e to the 13. Not the nicest answer I've ever seen. Actually, any number except 0 would have been kind of bad, actually. Nothing special about 13. Questions on that?
That's 5.4.
That's part of 5.4.
That's the algebra part.
That's the algebra part. Now what do we have to do?
Calculus.
Calculus. So what sort of things do we do in calculus?
Integrals.
We do derivatives and we do integrals. This is getting, oh no, we like the derivatives, because what was the derivative of e to the x?
E to the x.
E to the x. We like derivatives. Derivatives are good. What's the integral of e to the x? E to the x. So integrals are good too, aren't they? Well, how hard can this be?
Would it be
Technically, it would be e to the x plus c, yes. But what's going to happen? What if you don't have just the letter x there? What if I give you f of x is e to the 6x? Then what would you have to do to take the derivative? You have to use the chain rule, absolutely. So what would the derivative be?
6 e to the 6x.
Absolutely. You take the derivative of e to the 6x. The derivative of e to the 6x is e to the 6x. But then you have to use the chain rule and take the derivative of the exponent. And the derivative of the exponent is 6. So 6 e to the 6x. What if g of x is e to the sine x? Then g prime of x would be cosine x e to the sine x. Where'd that cosine x come from? That was the derivative of sine. So the derivative of e to the sine is e to the sine, and then you have to multiply by the derivative of the exponent. The derivative of sine is cosine. How about h of x equals x squared e to the x? What are you going to have to do to take the derivative of that function? That's a product rule problem, isn't it? How do you know it's product rule? There's multiplication, x squared times e to the x. H prime of x is x squared times e to the x plus 2x e to the x. Not so bad, right? So far? Yeah. How about g of x is, oh, I don't know, give me some function with e's in it. Make one up for me. Arctangent, we don't have a rule for derivatives of arctangent yet. 13 e to the
No.
Yeah.
e to the e.
3x.
Is that e raised to the 3x, or is that e times 3x, or does that 3x go down here?
E plus 3x.
Yeah, would it water
Plus?
around that?
You want plus?
No,
Okay.
I'm talking about like in the exponent. For e.
Oh, I like-
E to the e plus x.
I hope none of you
Yeah,
guys
what
are
if-
becoming math
What if it was e to
teachers.
the e plus x?
Hypothetically speaking, if it were 13e to the e to the 3x, would the 3x just like waterfall down to e to the x? How would-
Let's do this problem first, and then we'll do your problem.
Okay.
Because mine's easy. Yours is hard.
How splendid.
J prime of x is, what's the derivative of 3 times e to the e?
Wait, that's 3, not 13.
Oh, okay. What's the derivative of 13 times e to the e?
13 equals
Nope.
0.
It's 0. Why is it 0?
Number.
It's a number. There's no x's in it.
8. Oh,
This is a number. What's the derivative of a number?
true.
0. What's the derivative of 3x? 3. See, I told you my problem was easy. There's no x's in it. That's a constant. The derivative of a constant is 0. All right, so now your problem. K of x. You wanted e to the 3x?
Yes.
All right. It's okay? I don't know that it's okay, but we're going to do it anyway. K prime of x is?
Chain.
It's chain rule, all right? So I start with the thing furthest outside, that's this e. What's the derivative of e to a power? It's e to that power. So I'm going to have e times e to e, I'm going to have e raised to the e to the 3x. But then I have to take the derivative of the power. So then I need to multiply by the derivative of the power, which is e to the 3x.
E to the 3x times 3.
So our final answer is e to the 3x times, you told me the derivative of e to the 3x was e to the 3x times the derivative of 3x, that's 3. So that's a double chain rule problem. It's actually not so bad. It looks a lot worse than it is. It's a double chain rule problem. You leave the e to the power alone, you take the derivative of the power. And to take the derivative of the power, we had to use chain rule again. Questions on that?
I thought for the chain rule you brought down the exponent first and then did the
When do you bring down the exponent? When the exponent is a number. Is our exponent a number? No. Okay. All right, last question for the day. Determine where f of x equals x squared e to the 3x is increasing and decreasing. Standard Calc 1 problem. The only difference is in Calc 1 we didn't have e's, but we always did increasing and decreasing, didn't we? How do you determine where a function is increasing and where that function is decreasing?
First degree.
You take the derivative. F prime of x is x squared
3e. 3e to the 3x.
Okay, I wrote it as e to the 3x times 3, same thing. So I left the first one alone, that's x squared. I took the derivative of e to the 3x plus
X squared.
2x e to the 3x, because that time I have to take the derivative of x squared, and then I leave the e to the 3x alone. Okay, so now I take my derivative and I set it equal to 0, right? So that's 3x squared e to the 3x plus 2x e to the 3x equals 0. How do you solve that equation?
That doesn't work out.
Took it into Wolfram alpha, that would work, but I don't have that with me. Can I factor out? I can factor out e to the 3x, okay. E to the 3x times 3x squared plus 2x equals 0. How does that help?
You divide by the e to the 3x and get 0 again.
How come I can divide by e to the 3x?
It's a number.
Oh,
It's a function. It's got an x in it.
You divide by 3x squared plus 2x. Get rid of that.
I can't divide by that. I can't divide by that one. I can divide by this one, though, which is unusual. E to the 3x, when is e to the 3x equal to 0? Never. So how is it going to factor into solving this equation? It isn't in any way. E to the 3x can never be the number 0. E to the 3x is always positive. So if I want to, I can divide by e to the 3x. I can't divide by 3x squared plus 2x because that sometimes is 0. And then I would be dividing by 0. The point is, I can ignore this e to the 3x. I don't need it. It cannot be the number 0. It can only be positive. So all I really need to solve is that nice little quadratic equation. E to the 3x really doesn't factor into it. How do you solve that nice little quadratic equation?
Factor out an x.
Factor out an x. X times 3x plus 2 equals 0. So x equals 0. X equals negative 2/3. I draw myself a number line. I mark down the number negative 2/3. I mark down the number 0. I pick my favorite number in the world, bigger than 0. 1. I take 1 and I plug it into my derivative. Here's my derivative. When I plug 1 into that derivative, am I going to get a positive number or a negative number? Positive, because this is going to be 3 plus 2, that's 5. E to any power is always positive. Positive times positive is positive. Increasing there. I pick my favorite number in between negative 2/3 and 0. Negative 1/3? Negative 1/3 would be in between negative 2/3 and 0. Halfway in between, in fact. What happens when I plug negative 1/3 into that e thing? It's going to be positive. That's all I really need to know. This e thing is always positive. I plug negative 1/3 into here. I'm going to have 3 times 1/9. That's a third. And then I'm going to have plus negative 2/3. A third plus negative 2/3. That's negative. So I've got negative times positive. That's negative. Decreasing there. And finally, I pick my favorite number, smaller than negative 2/3. Negative 1. Although negative 13 would work, but I don't feel like squaring negative 13. Although, that's not so bad, 169. All right, I plug negative 1 into here. This one's always going to be positive. Really don't need to worry about that one. Plug negative 1 in here. I'm going to have 3 plus negative 2. That's positive. Increasing there. So there's my answer. Concavity would work the same way. You would take the second derivative, and what's going to happen after you take the second derivative is you're going to be able to factor out an e to the 3x. And then after that, that e to the 3x really doesn't matter because it's always positive. You'll just have to deal with the polynomial that's left. Okay? So e's aren't nearly as hard to deal with as people think they are. For the most part, you can ignore them once you've done your derivative and factored them out.
Where does the value for e come from?
Where does the value for e come from? That's an excellent question. What's the ln of e? It's not 0. ln of 1 is 0. What's the ln of e? Why? Because an e to the 1, they're inverses. So e, the value of e comes from, it's the solution to that equation. And then it turns out that it's an irrational number. It's about 2.71 something, something, something. Okay? So that's where the value of e comes from. Later on in this course, pretty soon, somewhere in chapter 5, we'll talk about exponential functions with different bases. So we'll talk about having 2 to the x or 5 to the x. And we'll actually develop a way to get an approximation of e. And we'll see what it's close to. Other questions?